Okay, we are ready for our next and last speaker, Professor Cyrus Shahabi from the University of Southern California. His talk will be on privacy models and neural aggregation from synthetic mobility to Geo-Scale foundation models. Of course, Cyrus Shahabi is, as I said, Emmett Jones, Professor of Engineering and the Director of Integrated Media Studies, Integrated Media System Center at USC Viterbi School of Engineering. He also served as the USC Thomas Lord Department of Computer Science from 2017 to 2022. He co-founded two startups, Geo-Assemble Technologies and Tallygood, which both were acquired in 2012 and 2019, respectively. He has a BSc from Sharif University in Iran, and also a PhD from the University, a master's at the University of California. Many patents, 14 patents, books, research grants from NSF, NASA, DARPA, NGA, DHS, and the industry, Intel, Microsoft, Oracle, and so forth. And he's very well known in the many areas related to the topics I mentioned, especially spatial algorithms and systems. And welcome, Cyrus, to this summer school.
All right. Thank you very much, Dimitri, for inviting me, and thank you very much for staying till the last lecture. I did not expect even that many people staying, so thank you. What I'm going to talk about mainly, the main topic is how we can release mobility data safely. And I kind of broke it into two pieces. One is on kind of more what we traditionally think of mobility data, which is location and aggregate location, like a number of people visiting a location. But then in the second part, we go more into real mobility data, where you have somebody going into different locations over time, and then how we can release that data safely. So in a sense, I think if you went to all the lectures so far, you already learned about location data, spatial temporal query from Professor Mokbal's lecture, or mobility and machine learning models to create these time series and spatial temporal data from Professor Salim's lecture, and then privacy just today from Professor Xiong's lecture. So this is kind of bringing all of them together, right? So we want to bring privacy into not only the location and mobility data, but also how to synthetically generate that. So that's really kind of the introduction to how this talk relates to some of the lectures you've been to so far. When I'm talking about these two, what I'm kind of separating things is the first talk is more about aggregate location data, as I said, and I'm going to use this logo for that. And then the second talk is sequence of locations. Let's call them trajectories. I'm going to define this a little bit more formally. So that's how we kind of differentiate the two talks. I haven't started my talk yet, so these are just introduction. So start by telling you a little bit what we do at my lab. So the name of the lab is InfoLab. And basically, we have a kind of a full stack solution. So we look into where the location data comes from. So it can, as you know, mostly coming from your phones with various sensors that you have on the phone. It might also be from the car, where you get like GPS location, like geographical coordinates, lat and long, for example. And this is where the location data starts. So we look at the acquisition of location data in our lab. So we actually work on that as well. And then once you have the data, how to store it, how to access it, how to analyze it. So most of my talk today is on this one. And then, of course, why you want to do that is at the end, you have all these actions. You have these applications on top of the analytics. I talk about some of these actually also as well, that why you want to analyze these, to maybe cluster them, to understand what mobility behavior people have and so on. So the main motivation of why we want to look at mobility data is that if you look at mobility data, how people move, you can learn a lot about their behavior, like people's behavior. You can learn about their shopping behavior, their entertainment, and their work commute and things like that. And once you know why people move, right, then you can enable a lot of applications. And I try to give you examples of each one of them, most specifically for the projects we are working on, so that you get a sense of what sort of things mobility data can enable. The location-based service was the most obvious one. I mean, you're probably using it yourself, starting from like navigation on Google or Waze, to, for example, these self-driving cars, the ride-sharing apps. I guess here Bolt is the more prominent one, but in US you have Uber and Lyft. In China you have Didi. So a lot of these are basically location-based services. They give you service based on where you are. Like Uber pick you up from where you are and then drop you off where you want to go. So the real physical location is important to these applications. Transportation is another area. As I mentioned, I'm going to look at these two logos. So from a trajectory perspective, if you have how people move and in a sequence of movements they have, then you have a lot of these for cars, let's say, then you can kind of figure out what's the traffic, right? Because you know how many cars are going on a certain segment at a certain point in time. So after doing some pre-processing and map matching and so on, you can basically learn about the traffic, right? If you have a lot of these trajectories of the vehicles and so on. The aggregate is basically can be used for traffic forecasting. So if you know how the traffic changes over time, once you have this at every point in time, then you can start forecasting, for example, how the traffic going to behave if there's an accident, or how traffic behaves during the rush hour and so on. I put some papers we have in case you're interested, but this one is actually interesting. This is the work we did in 2017 in ICLR, but actually the ICLR 2018, but this was a archive, and I want to make a point that the archive got a lot of citations. So don't always try to publish papers. I mean, putting a good paper on archive sometimes is good enough, because once you get a lot of citations, people would know the work anyways, whether it's get published or not. I mean, in this case, actually, this one did get published 1 year after. But this is just encouraging you to put the work out, and people would notice. Other types of data, other types of application, for example, is in health. I guess the obvious one during the COVID, everybody knows, like people use this location data to see, for example, how many people go to certain restaurant, or how many people go to certain store at what time, so that they can enforce policies and so on. And for the trajectories, if you actually know where how people move, you can see when they meet, and that's your contact tracing kind of an example. So that's a health application. There are also other type of a health monitoring application. So if you add wearable data to the location, like if you have an Apple Watch, and you can see basically what's the people heartbeat and so on. Again, from the aggregate perspective, you can, one example I usually give is that they have USC and UCLA. These are two universities in Los Angeles where they play football games. The average heartbeat of the students go up in the USC area. So you can basically look at these sort of aggregates. But of the same way, you can also look at people as they, for example, run. You can look at how their heartbeat changes depending on the location. And again, location is important, because if the heartbeat is higher when you're at a gym, it's less of an issue. But if your heartbeat is higher when you're home and resting, that's an alarm, right? So the location, in addition to the wearable data, actually can give you more information. These are just quickly some other applications. And again, these are the applications that actually work on. So they are as real as it gets, at least for us. But I'm sure that you guys working on similar applications as well, and can relate on how different types of mobility data can help. So with that, I think I was trying to basically motivate you that mobility data is important, and we can use it for all sorts of applications, from health to environment to location-based services. And there are actually a lot of location data nowadays available, either implicitly from Twitter or X, I guess, and others, but also explicitly sometimes people share their locations. But the problem is that also the location data is very sensitive. I'll tell you more about this sensitivity part in my talk, but basically because this data is sensitive, the issue is that how, as Professor Xiang mentioned, utility versus privacy, right? How we can still utilize the data for all these applications that are important, but at the same time respect the privacy of people. So that's really the kind of the introduction to the two talks, right? That why we are looking at this. So as I mentioned, the first talk, which is now the first lecture, is on aggregate data and these privacy models in general. So I can define what do we mean by location privacy and so on. And then later we look at the trajectories. So the easy example for privacy and location-based services is basically the typical scenario that you have a bunch of locations like hospitals and restaurants and repair shops, and then you have some sort of a location-based service or location server, and then there are users, whether they're in the car or walking around with their phone, and they kind of either explicitly or implicitly through their navigation app ask some sort of a question like, where is my nearest restaurant, right? So that's a typical query for these location-based services. Or they might ask for my nearby friends, for example, that in this case, the point of interest is moving. And the idea is that if somebody is listening to this kind of a query, just from the query and the results, it can figure out your location, right? And that's the privacy issue. The privacy issue is that once somebody learns about your location, basically they can stalk you, right? I mean, because it's very easy, it's very cheap to find this. It's stealth and it's ubiquitous. Everybody's sharing their location, and people started realizing this as the more and more apps and location-based servers become available about these privacy issues that having your location. What sort of things people can do by accessing your location. These are some examples from early days when people started realizing that what sort of attacks can be done once the location is revealed. And the more kind of a scary part was that you might be okay with your location being shared with Apple and Google because you say you trust them, but they actually were selling your location to third parties. And that was happening also behind people's back. So that was also at around 2010, people started realizing about these, the fact that these locations are being shared. So all of this resulted in around 2011 that they put some rules that this was the Location Privacy Protection Act of 2011, where they basically say the companies need to have the consent of the user in order to, if they want to sell the location data to third party. And as a result of that, basically there was every app that you download that has a specific location tracking, you needed to give consent that before your collection data. And this was not the case before 2011. So I remember the old days, you even download a flashlight app that has nothing to do with location, and it would automatically start collecting your location data. But then they asked them to actually have this consent. So the consent at the time was kind of very simple. You basically have this, and everything was check marked by default. And if you don't accept it, you basically couldn't download the app. So once you download the app, it automatically assumed that you will get all these checked and allow it to work. But nowadays, it's getting a little better. So this is the more recent. You've probably seen that when you download an app, it's asked, for example, whether you're can use the location during the time that you use the app or all the time. So this become basically the thing that, okay, now everybody knows everybody's location, and people started getting kind of used to this idea of that everybody's tracking your location data. So the question I have for you guys is that if I anonymize your identity, so I don't know this is your location, so I don't know who you are, I don't have your ID, but I just have the location, is that good enough? Is that solve the privacy issue? So would you care if you just tell me your location like every day, wherever you go, without telling me who you are? Right.
Behavior, but I don't know if they can identify you specifically.
So the answer is yes, they can identify you specifically. So, and I give you the kind of idea, and this was based on a paper actually published in Nature in 2008, which basically said if you have 4 locations, that's enough for important location, most frequently location that you go to identify you. And this is assuming some background knowledge. So for example, if I have this point as, so let's say supposedly my location, and then you see that overnight from like 10 p.m. or 9 p.m. until morning is at this location in Irvine. And then during the days at this other location at USC, these are like cities in LA, and USC is the university. You can, just from those 2, you can kind of start predicting, okay, this is Cyrus, right? I mean, you can look at background knowledge and figure out the identity, right? So actually just having location is enough to identify people. So as far as if you guys fill out IRB forms, they basically say that if the data that you're collecting can be used to identify people, then there you have a whole different set of rules to go by. And in the case of location, you can identify people. But then things actually gets worse, because once you find people's location, then you can start learning more. Like, for example, if you see someone going to their location is close to their church on Sundays, for example, you can figure out their religion. If you see somebody's going to, for example, a cancer treatment every six weeks, you can learn about their health status. So you can start learning a lot just from the location. Actually, if you have a bunch of people's location, like what Google has, you can start learning that who hangs out with whom, right? So you can even figure out a real social network, not the social network that is virtual like Facebook, but the real social network of who you hang out with just by looking at your location. So location data is actually very sensitive in that sense, because you can learn a lot. So because of that, people started working on how to make this location data private. So I'll talk about these privacy models next to give you some idea of how people started to looking at this. And then towards the later, or at the end of my talk, I talk about the specific work that we did, which is using neural networks for privacy. And in this case was for privately releasing the aggregate location data. So looking at the privacy models, there are 2 types of system model. I'm going to go through each one of them one by one. The first one is the online setting. And then let me basically tell you what the online setting, maybe actually. So the online setting, the idea is that the question is that where is the trust here? So in the online setting, you don't trust the location-based services itself, right? So if this is like Google of the world or Uber of the world, you don't trust them, right? So basically in the online setting, you want to, as a user, you don't even want to share your location with the location-based service provider. So that's the online setting. In the offline setting, you trust the location-based service provider, like for example, Google and Uber. But once they build these models, like the ones that Professor Xiang mentioned, and then you release these models, then here is where the trust is broken, right? So you don't trust the people who use the models because they can do MIA, for example, right? So we first go with the online setting. In the online setting, there are various architectures. There's a third trusted party architecture, client-server architecture, and peer-to-peer. I'm not going to talk about peer-to-peer, but I talk about the first 2 on what are the settings. So let's look at the third trusted party architecture. In this scenario, as I said, these are the users, and this is your kind of the location-based service provider that has the database of all the location. And then where is the third trusted party in this scenario? There is no one yet. But what you do, you just add that in the middle, right? So you have some sort of a party that you trust. This doesn't work sometimes. There's a third party that you trust, and basically you want to share your location. You're okay sharing your location with this guy, but you're not okay sharing your location with that guy, right? So how this third party hide location? So the idea is basically you send your query, like what are the closest gas station with your location to this guy. Then that guy somehow blur your location, send the blurry information to the other guy. I'll tell you more about this. And then that location-based service provider provide the answer back. And then that answer, of course, is not correct. The location anonymizer correct it and send it back, right? And this is kind of more generic, but I go through the specific techniques of how this would work. So the most kind of, I guess, the first and the most typical approach is the location k-anonymity. The idea is that you want to kind of hide yourself between k-1 other people, right? Mm-hmm. So you said as long as the server doesn't know whether the query comes from me or any 5 people around me, then I'm good, right? I consider that my location is safe. So that's the first approach. And of course, if you don't find enough k number of users around you, you can basically just either drop the query or generate some fake queries. So let's say that this is the scenario, and I want to ask you a question, so pay attention. So let's say that this is you, and these are like the restaurants you want to query. So instead of asking what are the closest restaurant, what you're going to do, assuming this third party that you trust, you basically send your query to the anonymizer, and let's assume your k, let's say in this scenario, is 3 or 4 actually, or 5. So the anonymizer basically, when send the query to the server, it says that all these 5 people want to know what's their closest restaurant, right? So it's going to ask this question as if it's coming from 5 different locations, right? So it sends 5 queries. The location service provider give the answer back, and then the anonymizer knows which one is actually you, right? So because the answer you get back is 5 different restaurants, but it knows which one is you, so it narrow it down for you and give you the correct answer. So this is kind of the k-anonymity. Now, my question is that when do you think this k-anonymity is not working or is not good? What situation the k-anonymity, yes?
If the restaurant share data with the server.
Yeah, I mean, of course, if colluding happens, like the restaurant is colluding with the server, but I'm thinking even before that, assuming that everything here is working as is there a scenario that k-anonymity wouldn't give you enough protection? Yeah, exactly. Or actually the other way around. Not enough people, let's say this is the solution, right? The solution is that if you don't have enough people, you just drop the query, okay? The problem is this. Let's say you want to cloak your location right now, right? And your k is 10. And you send this query to the anonymizer. Are you happy with that, with k10? Here we have more than 10 people, right? So the anonymizer would know exactly where you are. It knows that you're going to be in this room, even though there are 9 other people around you, right? So the k works if it's spread it in a wider space, which is whatever space you want to hide yourself. But if it's in a small space like this and there are a lot of people, you're not really. So what would be the solution to that?
Might be complicated, but onion routing.
Oh, okay, so you're way ahead of me. But a simpler solution is basically the cloaking solution, right? The cloaking basically says that this guy, instead of when it says the query, instead of looking for k other people, it's just looking for an area around, right? Say within 2 miles of me, right? And instead of sending the anonymizer, instead of sending your lat and long or your point, it sends that box and say, I want all the restaurants close to this box, right? Whichever, like 1 mile and 1 mile the box is. And then the same thing again. The server give the answer is a superset of what you want, and then you get the kind of filter. What's the problem with this approach?
It doesn't give the closest and the farthest in the area.
It still does. I mean, so you still get all the answers, but then this guy can filter and give you the correct one. So in both scenarios, you will end up with the correct answer. Yes.
The cost?
Yes, the cost is always a problem. I mean, there's always an extra cost for privacy. But what is specific about the cloaking?
You can still identify the location of the people.
Or the other way around. If you're in an area which is only you're in the middle of desert, and the area around you is big enough, but there's nobody else there, then it can pinpoint you, right? So it's the opposite problem of with the k-anonymity. If you have too many people close to each other, here if you're in a big area, there's only you.
What about generated data for specific area that you can be lost in this?
Yeah, so creating fake. Yeah, so I haven't got to the solutions yet, but I'm just trying to motivate the type of challenge, right? That basically you have this issue of if you just do it based on space, you have some problems. If you just do it based on number of people around you, you have some sort of problem. So I want to kind of get to the point that you kind of need some sort of a hybrid, right? You need something that looks both at other people in the area as well as the space, right? So that was kind of earlier work, and they started figuring this out, right? That you need both to deal with it. So I'm giving you some examples. These are not necessarily the best work, but it's easier to kind of get you through this. So for example, the one approach that was trying to generate some sort of hybrid was that if this is you and these are other users, you basically, I don't know, you guys familiar with quad trees, right? So it kind of build a quad tree on this. Let's say that, for example, the K is 5. So you want to be hidden in 4 other people, I guess. So what it does is basically keeps doing partitioning the space until it comes to the point where you go less than K. So this is now you're only with one other person. This is less than K. So you go to an area above that that also support K. So in this case would be this area, right? So this would be your cloaked region, right? So it both has the space and has the number of people. Yes.
What's the enough amount of points to not identify you?
So K, that's actually my next slide. So K is important, right? So what is your K, right? I mean, or does everybody has the same K, right? I mean, and that's your level of privacy, right? So I might be okay with my K equal 2. You might want to be K equal 10. But in this work, basically, we assume everybody has the same K, right? Which is not ideal. So okay, this is not the next slide. This is one more approach with the same K, and then, but it's the same idea. It's just trying to solve it differently. Here, basically, you do k-anonymity. So the idea, for example, is if in this case K equal 5 again, you find 4 other users, and this becomes your set. Now, my question is that, oops, I give you the answer. My question is that, can I just do an MBR of these 5 people and send it? Is that good enough? So an MBR of this circle, the minimum bounding rectangle of this circle, is that my region? And I send it, is that hiding you? You're happy with that, with K equal 5? What's the problem with that? Well, the problem with that is that when you do that sort of a thing, most probably you're in the center of the box. And then the other problem is also the one that we already discussed, which is the K, if there are too many people around you, you're not really hiding yourself. So in order for them to solve that problem, they said they randomly pick one of the neighbors. So in this case, they randomly pick this one. Then they do the k nearest neighbor for this guy rather than that guy. And then they create a set that includes the nearest neighbor and the user, right? And then the MBR of that set is sent out, right? So this way, they basically prove that by doing that, they solve both problems, right? So that's another approach. So these are just to get the kind of the idea that what sort of things people were trying to do. And this is the point that you made, right? I mean, what if people have different Ks, right? So here is an approach for if you have different Ks, the click block. So let's say that these are different users and the K of each user is different, right? So they have different anonymity levels. And what we do is basically find the maximum cloaked area. So the maximum cloaked area for this guy is the space that there are, in this case, 2 other people, right, in that space, right? So you do that for everybody. So you find this maximum cloak area for everybody. And then you look at the cases where people, 2 people, I don't see this sometimes, or this doesn't show up. But let's look at A and B, right? So if A and B are the 2 people, actually,
The battery is running out. Yeah, because you used it extensively. Yeah. The battery is probably dead.
Yeah, I'm gonna use this, but just for the pointing.
Let me see. Let me find another battery.
Oh, this one doesn't even show at all. Okay, never mind. So I'll use my hand. So basically, oh, don't take that. So here A and B are the 2 that actually they are inside each other's circle, right? So in this case, for example, B has A in the circle and A has B in the circle. If you have a situation like this, you connect A and B together. Okay. So that's how you create a graph, right? So you keep doing that. I'll tell you at the end what happens. So you keep doing that for the ones that contain each other until you generate the whole graph. Now, if a new user come in, let's say a new user with the new K come in, then you basically, thank you. Then you do the same thing. You create the maximum cloak area for the new user, and then you find all the members that their K is less than the K of the new user. So in this scenario, only these 2 guys are less than or equal this guy. The other people that there are not. So once you figure that out, then you create a link between these guys, and then this box is what you send out. Now, I explained the technique, but I didn't give you the intuition for a reason, because I want you to tell me the intuition. So why do you think this is an interesting box to send? So this box basically says that because all of these guys are connected, they are in each other's maximum cloaked area. And there are 3 of them. So this is for user M, K = 3, so that's good. So the reason is that no matter which one of these 3 send the query, you always send the same box, right? So when you have these different Ks, this is a good property to have, because the server wouldn't know, because all 3 of them would end up sending the same cloaked area, right? So just from the cloaked area, I couldn't figure out who was the querier. So that's why, did I do something that EDBT can?
Yeah, you can press.
Now it's tagged. So that's this approach. There's another approach. I go through that one quickly as well. I have time. I don't need to go quickly. How many of you know what Hilbert curves? Oh, okay. Let me just show you what a Hilbert curve is. So this is a 2-dimensional space, right? And you have these dots, right? If I ask you to sort these, can you do it? Can you sort these dots in space? What's the first one? you can't because it's 2-dimension, right? I mean, so if I give you a bunch of people with their ages and I ask you sort them, you can sort them, right? The youngest one is first, and you just sort it. But if I give you things in 2-dimensional space, you cannot sort it, right? So people try to reduce 2-dimensional space to 1-dimensional space so that they can sort them. And one approach to do that is the Hilbert curve, right? Hilbert curve, think of it as a way of going through the space in a very specific fashion. But then it starts giving you an ordering. Like now you know A is first, then it's B, then it's then it's C, then it's D, E, F, G, H. So that's the ordering that Hilbert curve provides. So this is basically now the new ordering. And then each one of these they have a rank. So the rank of A is 0 because it's the first one in the Hilbert curve. So that's the sorting, right? So that's how you sort all these points from 2-dimension to 1-dimension. So this approach, what they did is that they first generate a Hilbert curve for all the users, and then basically say that to anonymize the user, we start from rank minus rank mod k. So let's just do that for an example. So here the rank is 3. 3 mod 5 is 3, right? And then 5 minus the 3 minus the 3 is 0, right? So that gives you the start point. And then start plus k plus minus 1 is 4. So basically from 0 to 4 becomes your cloaked area. And that box is basically your cloaked box, right? So what is the advantage of generating a box like this? Let me go one more example. So for edge, for example, if you want to cloak edge, you do the calculation again. 7 mod 5 is 2, right? And then 7 minus 2 is 5. So you start from 5 and then go, in this case, 5 more because the k is 5. So that's the cloak region for edge. So what is the advantage of this cloaking? So the advantage of this cloaking is that all the, for example, KU user, again, would have the same start and end. So the cloaking would basically be the same. So if you look at 5, for example, all the 5s would start from 0 until you hit the next interval, which would be from 5 to 9. And then you hit this next interval would be 10 to something, right? So always the start and end would be the same for everything that has 5, for example. And that generates, again, the same box. So anyway, don't worry about all of these. So these are just to get you a sense that people were getting very kind of innovative on how to do all this cloaking and k-anonymity, but all of that actually you don't need to worry about because the new approach is not based on that. But before that, let me give you a little bit of another quiz. So let's say that you start with this as a cloak region for A. So A send a query, you cloak it, and basically send a query from A, B, C, D, E, right? But then people move, right? They don't stay at the same point. So once they move, let's say that in time t plus 1, they end up like this. And you cloak it again. Now you send a query from A again, but this time A is cloaked with B, E, B, F, G, H. Does the server learn anything? Yeah, because I mean, now the server knows that at first it was trying to figure out between A, B, C, D, E, which one is A, right? But now it's only knowing that F, G, and H just showed up, right? So the query is between A and B. And then in the next time interval, only A is left with the cloak, and they figure out exactly who did the query. So all these approaches would start failing if you look at things moving over time. So possible solution is to just keep adding and increasing the cloak, which generates a lot of noise. So you want to, if you started with A, B, C, D, E, you keep A, B, C, D, E all the time in the region. And by doing that, what's happening is that you keep growing and shrinking your box, right? So that's against the idea of the box should be staying the same. All right, that's enough of the that, let's go to the client-server architecture. So with the client-server architecture, there is no third party, right? So it's just the users and the untrusted server. Any idea how can the user now cloak themselves if there's nobody, no trusted server in between? Or how can they hide themselves? So they can lie, right? So instead of saying that this is my location, they can give a different location. What should be the characteristic of this lie? I mean, what sort of location they should lie about? I mean, it shouldn't be that far, right? Because you still want to get the service, right? So here is an example. I'm actually going to show you with a slide, but basically the idea of lying is basically adding noise, right? So instead of giving your location X, you add noise and give a different location Z. And this is basically the lie, right? So what are examples of this cheating? Let me give you one example. So let's say you want to go for Uber ride, right? And instead of giving your exact location, you find the closest landmark to you and say, that's my location, right? So the landmarks, a lot of people show up, so that doesn't reveal anything, right? Because but what's the cost? But the privacy is good because you always give a landmark location and they can't figure out whether this was your house or your work area or something, right? What would be the cost of lying? Yeah, so the Uber guy gonna go to that landmark, so the cost is that for you need to walk to that area, right? To the closest landmark. So that's the utility versus the privacy issue, right? So that's one approach. But now basically we want some sort of a definition that captures this k-anonymity, the cloaking, but for this scenario, right, of adding noise. And this is where finally, basically, you have a formal privacy guarantee that combine all of these, right? It gives you the client-server architecture without the third party, and it would support your both cloaking and k-anonymity together. And this is called geo-indistinguishability. It's based on the differential privacy that Professor Chiang mentioned in her talk this morning. So let me tell you briefly how does it work. So you guys remember this equation from this morning. So this is your randomized algorithm. I'm calling it here a randomized mechanism, K. X and X prime are two locations. So basically, you want the same location Z be reported whether you give the location X or you get the location X prime, right? So this is the same equation with the same e to the power of epsilon, except this is new, right? And what do you think this is? This is the distance between X and X prime, right? So what basically you want these two different locations. What would happen if X and X prime, the distance between them is 0? It's basically the same point. But basically what you're saying is that these two are equal, right? So which is what you want, right? You want if X and X prime are the same location, Z give you the same, it basically always give you the same Z, right? But you also want to let people lie, right? And that's basically the noise, the e to the epsilon. And the way that e to epsilon works is the same idea. Epsilon 0 again give you the that you make sure this is the best privacy. So epsilon 0 is the best privacy, and the higher epsilon is basically a higher privacy budget, so it gives you less privacy. So here is so I already mentioned the distance thing. So here is the what things changes with epsilon. So if epsilon is high, as I said, the privacy budget is high, so it's less privacy. So what does less privacy means is that the difference between what your true location is and what your perturbed location is kind of within a smaller area around you. So it's one of these other locations, right? That's based on the distribution. I'll tell you what distribution this is coming from later. What would happen if I reduce epsilon? What do you think this would happen to these breadpoints? So blue is your actual location. The red is the lie that you're giving.
Closer.
It's actually spread out, right? Yeah. So because now you have, so by reducing epsilon, you mean you have less privacy budget, right? So it means that you need more private, right? To be more private means that you lie more, right? So you basically, your lying can go all the way around, right? So it's spread out. So the idea now is that if somebody, like from an attacker perspective, it knows for sure that you're, for example, in Los Angeles, but it doesn't know whether you're at USC or not, right? So the area that it can attack, it can figure out where you are, kind of gets spread out. In the previous case, it could have, for example, it could have figured out that you're in like USC area, you're in the middle of the map, right? But in the next, it's kind of spread out, so it can only figure out that you're within LA, but can't figure out you're in Los Angeles, in USC area. So that's basically the role of the epsilon. So where these kind of, how would you figure out what or where this kind of a noise coming from? So how would you know, for example, that you need to spread it out like this and generate these kind of a noisy data? So this is basically, you want some sort of a noise generator that satisfies the geo-indistinguishability, or basically differential privacy. And that's basically coming from a planar Laplace mechanism. So a Laplace, I guess this is a 2D Laplace, but it's basically very similar to the normal distribution or Gaussian, except that it's a little more pointier. So basically the chance of giving the correct location, this is 0, right? So you basically give, you don't lie at all, you give the exact location, is higher. And then the tail is actually more fat than the normal. So there is also a chance that you give some extreme scenarios. As you see in the previous picture, there are some cases that you give a very kind of a spread out location. So as long as you basically sample from this planar, so for example, if you want to report Z, instead of reporting your actual location, you add to it a displacement vector, is a 2D displacement vector, and this 2D displacement vector is sampled from this Laplace, right? So that's how you basically lie. This is just basically telling you that this is you're not generating two 1D planar, two 1D Laplace. You just do a 2D Laplace. And do you know why we can't do two separate 1D Laplace and sample from? Why can't I just do sample from X and sample from Y separately? Because X and Y are correlated, right? In real world, these are correlated. So you basically do it 2D. And then this is another detail, but if you ever want to actually implement this, you shouldn't really generate these, you shouldn't really generate these vectors, this vector displacement V, but you should actually convert it to the polar coordinates and then sample the angular and radial marginals. I mean, very detailed, but if ever you want to implement it, that's the way to do it. Okay, so just wrapping this up. So basically with the geo-indistinguishability, it's kind of a combination of both the cloaking and k-anonymity, and it also can be done in a client-server mode, right? You don't need a trusted intermediate, because you just add noise and send the query and get the results back, right? Based on the noisy stuff. But again, I guess as we heard this morning, the utility can be very poor in practice, right? And that's because you basically give a point that is not your actual location. And I will give you some examples later on how this would work with the noise. Can you do better using some knowledge of user check-in behavior and improve the utility? So the idea is that when you generate these noisy fake locations, there are certain locations that people never can go there, right? You might end up putting, for example, location in the middle of the water, right? So by kind of reducing that, you can improve the utility. So some people did that. All right, let's move on to the offline setting. So the offline setting, the trust barrier comes here. So you basically say, okay, I am okay giving my location to Uber because I'm getting service back, right? I'm okay giving my location to Google because I can do navigation. But I don't want them to generate a model based on my location, for example, or do some aggregation and then release this aggregation data because I don't trust these other people who use the aggregated model or you use this neural net, for example. Why do you not trust these guys? What these guys can potentially do, because your data is not being released, you're releasing some aggregate data, or you're releasing a model. Yeah, they can do the MIA attack, right? I mean, they can basically use this model that your data was in it and do a inference attack, right? Membership inference attack. So how would you, so in this next part of my talk, I basically say, how would you protect against that? So as, again, you saw in the morning, there are companies who actually released location data during COVID. And this includes Facebook and SafeGraph. How many of you heard of SafeGraph? SafeGraph actually released a lot of aggregate location data during COVID, and the data used for in a lot of actually research papers, which basically says, for example, how many people go to certain locations like restaurants and so on at certain point in time. Census actually also released a lot of location data, and all of these guys use differential privacy. So they all added noise, and they basically they did that to basically say that you cannot do MIA, right? You cannot do membership inference attack and figure out the location of the people who are used to generate these aggregates. And that was the reason that they released the data, and they were confident that people wouldn't figure out. But the problem with these releasing aggregate, and I give you a simple aggregation. The simplest aggregation is basically counting the number of people that are in certain area and just release that count, right? So for example, you can take a space and put a grid on it and then count the number of people in each cell and then release that information, right? So that's the simplest model. Basically, it's just a simple aggregation. And then the idea is that what you do in order to provide differential privacy is that for each one of these counts, for each cell, you add noise, right? So instead of releasing the actual count, you add noise and release that value, right? And this would be differentially private because now you added the noise. The noise, again, can come from Laplace distribution, and you can basically prove that this satisfies your differential privacy. But the problem is that if I query and say, okay, how many people are in this area, and I draw a box, but these boxes don't align exactly with the grid cells, what would happen? So basically, I ask a query, and my query is in this area. So it includes, like, it doesn't start from it's not aligned with the cells. It starts from the middle of the cell. How would you count the number of people in that box? So for the cells that are fully in the box, you just add them up, right? So that's easy. For the cells that are not fully there, if like 1/4 of the cell overlaps with the box, you just take the count and multiply it by 1/4, right? And say that's the number of people there. What assumption you made? Yeah, you assume that the number of people in that grid cell are uniformly distributed, but that's not the case, right? So you actually have extra error. So depending on how you partition the space, you change that error, right? So you have now two sources of error. One is the noise, which basically you need to add anyway, right? Because of differential privacy. but one is also this extra noise that you get, extra uncertainty you get because of the partitioning of the space. So people actually in the database community, they published a lot of papers looking at different partitioning and trying to solve this problem, right? Because this query, if I ask you how many people are in this box, it's a very important query, and it's already noisy because of the noise you add for differential privacy. You don't want to add more uncertainty to it because of the partitioning. And we included, actually, we did a paper on this as well. But then recently we came up, I mean, this is like a couple of years ago, we came up with a kind of a totally different approach, kind of out of the box approach that worked much better than all this partitioning. So I'm going to tell you a little bit about that and show you how that improved everything. So again, to kind of explain the problem, we want to do the range count query. So given a range, and we define a range by C and a R. C is the corner point of your box. Let's assume without the loss of generality that this is always a square. So C is basically the corner of the square, and R is the radius or the size of the edge. And you're asking how many people are in this box. That's your query. That's your range count query. And you want to do this satisfying the epsilon differential privacy that you heard about this morning. What is the data? The data, the true database is a bunch of points. Basically, each point says that somebody was there at that point, right? So if you want to count it, let's assume that you put a 2D partition on it and then count the number of people that are in each partition. And we just color code them based on the number of people. Like, for example, this box has 120 people. This box has probably around 60 something people, and so on and so forth, right? So this is your database. Now you're going to do the range aggregate query on top of this database. You want to count the number of people in a box. But you don't want to do that on the original data because you can do inference attack, right? And figure out if you were there or not. So you were doing it instead on a noisy version. The noisy version add noise from a Laplace mechanism, in this case, a function of epsilon. Don't worry about where that 1 over epsilon comes from. And you get this noisy histogram. This is now differentially private compliant because you added noise, and you can release that and you can answer the queries, right? So what would happen if you're basically looking at the privacy and utility from a utility perspective? If you ask a question from this noisy one, this is the answer you get. And if you do it on the correct one, that's the answer you get. The difference between these two is the utility of your query, right? So you basically want the answer you get from the noisy, which is Y, be as close to the real answer as possible. Oh, and then one thing which is important is that once you have a sanitized data like this grid cell, based on the post-processing property of the differential privacy, you can do any future computation on this and it's still going to be private, right? So you can do whatever you want once you release these. So what we did was that we said, okay, we take this noisy grid, which we basically know that is differentially private, but probably the utility is not very good, and use this to train a neural network. And you can think of it the way you train it, the neural network. Actually, I have a slide for that. So let's say this is a simple neural network, fully connected. What it gets as input is the lat long, which is that C, and then size, which is the R of the box, right? So these are the three inputs, and the output is the result of your query, right? How many people are in that box? Okay, so you basically, your training set gonna be, and this is gonna be trained on the one that is already noise added, right? So this is a differentially private data set. So you basically train this, let's say, for example, you get a C, you get an R, and you train it, and you say the result of this based on the histogram, which we added noise, it would be certain value. So you get the model output would be 32, but the histogram would say that no, the real answer is 45.8. So you use some sort of a loss function, you do gradient descent, and do this continuously, right? So this is how you train this model. The actual loss function and training set is different. If you're interested, you can read the paper for the details, because that by itself is actually a technique. It has other applications. But let's go back to this. So now my question is, so you take this noisy thing and then you add, you train it using this neural network. So this is the neural network, you train it with this noisy. And now my claim is that if you do a query, right? You ask a box and say how many people are in this box. You can ask the query here, that gives you the exact answer, right? But it's not private. You can ask the query here, it gives you some answer. Or you can ask the query by doing a forward, pass forward on this neural net, right? Because now this neural net is trained. So you can pass your query as the C and as the lat long and the R and ask the query here. Which one you think would give you a better, more accurate answer of your count? I mean, of course, this one doing it directly on the original data give you the best answer, but it's not private. But I'm asking between asking the query from the neural net versus asking the query from that noisy grid, which one would give you the better answer, the more accurate answer? Yes. Yeah. So why? Because that's a little counterintuitive though, right? Because we use the noisy thing to train the neural net. But now we're claiming that if you ask the question from the neural net, you get a more accurate answer than asking the question from the noisy. Why is that?
Because of dropouts resist noise.
So what you learn actually from the morning lecture about neural nets, about this kind of the pattern and then memorizing, right? Yeah, so before overfitting, what do you have? You have the pattern, right? So the reason that this works is because the neural net captures the pattern, not the noise, right? So what you did was that there was a pattern already. There was a pattern already here, right, in the original data. Then you added the noise to kind of remove the pattern, right? But then you use this noisy data to train the neural net, and the neural net only learns the pattern, not the noise. So in a sense, what it's doing to the noisy data is denoising it. So the neural net, in a sense, is denoising the noisy data that you added because of the privacy. So here is to show you what's happening. So this is the original data, right? So you see in the original data, the counts, there is some pattern, right? So there are certain numbers. This is synthetic data. It's just Gaussian mixed model, basically. So these are the original data. Once you add the noise for differential privacy, it looks like this. So, but the patterns disappear once you add the noise, right? But then when you use this noisy data to train the neural net and then ask the questions from the neural net, it looks like this. So in a sense, it kind of recovered the pattern of the data. So it kind of denoised it. So that's why you do the query here, right? You get a better answer than doing the query here. And the good news is that this is already differentially private. So everything you do afterwards is still differentially private. So we did this like on different types of patterns, and you see the same effect, right? So you see that the noisy thing here basically covered the patterns, but then the neural net actually recovers the pattern. So what you want to make sure that doesn't happen here with your neural net from the morning class? I guess you kind of mentioned it. Yeah, you don't want it to overfit. What happens if you overfit?
Memorize.
Yeah, it memorizes the noise. And that was the whole point. We didn't want it to memorize the noise, right? So we wanted to actually only memorize the patterns, right? And that's what exactly, so if you read the paper, it's all about how you basically stop the training at the point that it captures the pattern, but not the noise. Now, if you listen to the morning lecture carefully, you probably can answer this question. But so the idea was that it's a test, yes. So the idea was that you added this noise because you want to make things private, right? But then we said, okay, this neural net now denoise it. Is it that we just make this not private anymore? I mean, basically say, hey, here this is the amount of your noise you need to add, and we just added the noise to all these cells, and then we use the neural net to capture the pattern, and we said we kind of denoised it. So is this data still private? Yes, because I guess again, because differential privacy says that once you add the noise and you basically get the differentially private grade, everything you do on top of it is still differentially private, right? And we didn't do anything more than just querying it and basically using that query to train a neural net. So why do you think that, what actually happened then? Why this denoising is not bad? So the real answer, I don't know, but the speculation is that with differential privacy, you add too much noise because you do it based on sensitivity of the query. And the query here, and that's where that 1 over epsilon comes from. 1 is the sensitivity of the query. And the query here is count query, right? The count query basically says that, you remember it was D and D prime, the two databases, that they are different in one person. So the count query, that one person can change it, right? If you have that one person, the count might be 4. If you don't have the person, the count would be 3. So the sensitivity is 1, right? So that's where that 1 comes from. So because of that, it looks at the very kind of extreme scenario and add that much noise to kind of cover that, right? So it add excessive noise. And what this neural net is doing is just basically taking the excessive noise out, right? But still the data is private. So the required noise is still there. And that's why it's still private. So basically we did some tests. So these are actually real data. Veroset is the raw data for SafeGraph. It's basically 10% of the US mobile devices in 2019. We had their check-ins over time. And we also used some public data set like Gowalla and the taxi rides in San Francisco as the location data. These are real location data. These are some of the statistics of the location data that we used. So it's basically very different types of location data. And then the query was, we generated randomly 5,000 range aggregate query, range count query, and this basically centered at uniform random positions with different size. So that's the C, and this is the R, which is the size of your box. And the metric was the relative error. And we did like 2,000 of these from sample location from the same distribution. So the result was basically with the SNH model. SNH is the neural net that I was talking about. It's just a fully connected network with 20 layers this is just the model depth versus the relative error. I think this is not important. This is what I want to focus on. So you remember I told you that there are a lot of techniques out there. So these are all the other techniques that before SNH was published in various database conferences. And if you look at them, this is basically epsilon. So as you increase the privacy budget, the error, of course, as you increase, the error gets better. Because you increase the budget, you basically means that you have less privacy. So error gets better for all of them. But if you look at them, each one of them, these are different cities, they are all pretty much improving on top of each other in a very marginal way, right? But then you look at SNH, which is the neural net approach, and it's a big jump, especially in these low privacy areas where epsilon is small, right? And you see a big difference between SNH and these others. So as I mentioned, all of these others were trying to change the partitioning, and we used a very simple partitioning. We just use grid. And by just doing this simple technique, it actually outperformed all the others. We also extended it for time. So when I mentioned this number of people in certain area, nobody asked what number of people in certain area at what time. I mean, I mean, because just counting the total number of people over what period of time, it's not that interesting. But you might want to say, okay, I want to know how many people are in this campus between 10 and 11 a.m. on Saturday, right? So the real query, the real range count query has a time aspect to it as well. So it's time and space. So we did that for, we try to apply the same. So basically, if you think of the 2D being the space, now you have a third dimension, which is time. So if you slice it, each slice is basically the one of those spaces, the 2D spaces for a given time, right? This is actually, this is Tokyo, and each dot is the a person tweeting at a specific time in Tokyo. So you see that how it changes. And the shape is basically the shape of the metro stations, metro lines in Tokyo. If you're familiar with Tokyo, this is the Hamano line that goes around Shibuya, Shinjuku, and so on. So in case, so this is basically your 3D space, right? Now you have time as well. And if you ask the question now, the question is that how many people are in Japan at Shibuya station at this time, 10 to 11 a.m., right? That's your range query now. And this has a lot of applications for hotspots and things like that. I already mentioned some of the applications in the past. So how we do this now is very similar again to the same idea, except that now you have the time. So for this part, for the space, if I want to, so in the previous work, we used the fully connected neural net. That was just a simple approach to make the main point. But if you want to capture the pattern of a 2D image like this, what neural nets you would use? You guys are familiar with neural nets. So this is I kind of give the hint. This is an image, right? CNN, right? So a CNN basically is a convolution neural network that specifically for images. And you might say, well, this is not 2D, or this is not the Euclidean space because you have these like stuff. But that doesn't matter, because if you think about it, the aggregate is still going to be on a box, and the box is going to be on top of this 2D space. So you can think of these grids, the same grids that you've seen before, and you do a convolution neural network. But then what about the time aspect of it? So you do convolution neural network on each image, but then how you deal with this over time? So what we did, I mean, how many people are familiar with variational autoencoders, VAEs? So we basically use VAE, but if you're not familiar, let me just kind of give you a very simple explanation. So the idea is that you take these training data. These are your cuts on your slices on the 3D cube that I mentioned. And you kind of think of it as you encode it to a smaller space, that's Z. And this Z is a much smaller space, right, than all the images. And then you decode it back to the images, right? Now, in this process, you want these decoded images to be as similar as to the encoded images, right? So your loss function basically says that I want minimize the reconstruction loss. So I want this image to be the same as this image after it goes through this smaller kind of encoded space, right? So by doing that, what are we forcing to happen? I mean, by optimizing this reconstruction loss, but kind of condensing, think of it as a compression, compressing this into this smaller space and then decompress it back, what are we achieving? It is embedding, but I mean, what in the context of what we were doing with the noise, and because these are noisy images, right? These images, we added noise because of the Laplace to make it differentially priced. Yes? Yes, in a sense, basically, because when you want to compress something and then decompress it and regenerate the image, what you need to capture is the pattern, right? So you end up forcing this to capture the pattern, but not the noise, right? So it is kind of denoising it, right? And again, it's the same idea that you want this to happen without overfitting, right? Yes.
Would any form of lossy compression work?
That's a very good question. So any lossy, that's the key, right? But in a sense, you want the problem with the lossy is that they basically try to learn from like they don't learn from the data itself, right? They just have an algorithm that does the compression, but you want it to learn from the images. So that's why these neural nets work, because you here, for example, what would happen is that if you look at different patterns of Tokyo, for example, it would learn that these are the areas that changes from one time to the other, right?
It's because, like, let's say I'm doing dimensionality reduction.
Right.
I'm still trying to keep like most important features.
Right, but then you're not learning from the data itself, right? You have an algorithm that basically just do the compression. But in a sense, I guess the idea is the same. But the problem is, again, as I mentioned, you don't want to learn, you don't want the compression to basically learn the noise, right? And keep the noise. You want it to keep the patterns. That what is the pattern that basically from one time to the other stays, right? And capture those. It's kind of like an MPEG type of a compression, which takes the time into the consideration as well. So it's both the space and the time. So it's not a single image. So you want to take the correlation over time as well. But also you want it to learn depending on different data sets, right? But yeah, I mean, the general idea of compression is actually might work. But yeah, so as a result of that, what happens is that, so I was saying that we want to also remove the overfitting. So if you look at VAEs, instead of having, in addition to having a reconstruction loss, there's a regularization loss. So this is what we actually worked a lot on to avoid the overfitting. So we even, if you're familiar, we use a quantized version where you have a discrete, basically, space to make it less, giving it less information for the noise and keeping just the patterns. Still have 15 minutes, right?
Yeah, that's correct.
Yeah. So so again, I mean that was the same idea, except we just improved it both for time and space. Because these are, and this approach, so the previous one we call it SNH, this one is VDR, and this is appeared as a paper later after that, to basically based on VAE, and it results actually was very good. So on each one of these we do convolution, and then across these we do this compression or encoding decoding. Oh, I don't have results on this one. I think I finished earlier,
Okay.
but I can go on the second one. Or just
Whatever you prefer, we can have a break now and then continue. It's like equally spaced.
I can either way.
Yeah.
I said somebody
Okay.
said no, I don't know to which one though.
Yeah. So let's have this. Do we have questions first of all?
Do you want to do a 45 minutes break, or you want to do shorter break?
No, we do a 30-minute break. Yeah.
Oh, okay.
Yeah. So do we have any questions from the audience? No? Okay, then let's think there is
All
a
right.
speaker and move on. So we make a 30-minute break and then be back. No, 4:15. Okay, thank you. We're ready to move on to the second part of the talk. Yeah, unmute. That's great. Okay.
All right, so just a quick kind of overview of what we discussed already. We said that we have a lot of location data and there are a lot of useful applications that can use the location data, but because of the privacy, we want to make sure that we can release this location data to be used for these applications, but at the same time respect the privacy. In this talk, I basically moved from a single location, which was what we were focusing now, to a sequence of location. So here basically is what is we call trajectory. It basically you're at this location at this time, then at this location at this time, and so on and so forth. So you have a sequence of location. So the outline is that I motivate why basically you need these trajectories, give you a little bit of background, and then talk about two types of ways of generating these sequence of locations. So to motivate it, basically, why would we need synthetic trajectory generation? So as I mentioned in the previous talk, if you have large amount of high quality data, you can basically learn model the human mobility, and this can be used in various applications. But the problem is that unless you're Tesla or Google, you don't have large high quality sequence data, right? So for example, if you're in academia, because of various concerns, privacy is one of them, but basically you don't have the money to collect that much data. There are a lot of confidentiality issue and so on. You end up with small or low quality data. So this is what we have in academia, at least, or most companies, and this is where we want to be, right? And the idea is that can we take our data that is low quality and either fix it, or if it's a small amount of data, scale it up. So synthesize data that now this would be the good data that we can use for training our models, right? So that's the idea for generating these synthetic trajectories. So this is not new, the concept of generating synthetic trajectories. If you're familiar with the early works in this moving object community, there are basically algorithms that basically try to generate the synthetic trajectory algorithmically. And they used various type of travel survey or handcrafted rules to figure out how basically objects move in space. And then they generate this sequence of object movements. If you are in transportation community, actually, there are a lot of simulations out there. They call micro simulations or agent-based simulations. And they also take this aggregate information from similar sources like travel surveys and so on. So basically say that there are this many people at this location, and then there are this many people at this location at time t+1. Therefore, they moved from here to there. There's the road. So this is how they moved. And they basically simulate these movements of the agents or vehicles. But both of these basically require a lot of human in the loop. Basically, you get this aggregate data and from those you generate these parameters of your simulation. And if you're actually familiar with this agent-based, there are a lot of papers just to explain how you go from this aggregate data to the parameters of your microsimulation. So figuring out the parameters by themselves are actually a lot of work. So the idea is that can we remove the human from this loop, right? Can we basically go with some sort of a data-driven approach where you take the real data and send it to some sort of a learning algorithm instead of sending it to human that generates the simulators and the parameters, and that generate the data, the synthetic data directly. So this is kind of the concept of the synthetic trajectory generation, and this is how it's different from the previous approaches of the agent simulators and so on. So the idea of this generative AI is basically, can I generate these movements synthetically? So imagine this is your word again as a grid. And imagine each cell basically is the probability of somebody visiting that cell. So in order to generate a sequence of movements, what you can do is basically generate the first location that somebody visits randomly based on these probabilities. And then say, okay, now if you're in this location, what would be the next location you go, right? And that would be your next location. And then you say, okay, if you start from here and then you're here, where are you going to go next? And so on and so forth. And that become your trajectory, right? That become your sequence of movement. What this reminds you of? So first of all, this concept of generating one location at a time is very similar to the concept of ChatGPT and generating one word at a time, right? So there's that aspect of it. The other aspect, I guess, this by itself, I guess, should remind you of chess, right? So with chess also, you have these movements and these rules, right? That you go from one location to the other based on some rules. So in a sense, basically, we want to try something similar to generate these sort of trajectories for us based on some policies. Like if chess is, the policies are these rules that are given, but in real world, the policy is the decision that then a user, a real person takes by going from one location to the other location. So you want to learn those policies. So early work basically was the work of sequence GAN. GAN stands for Generative Adversarial Network. And the idea is that you basically have two components, the generator and discriminator. The generator tries to generate these synthetic trajectories or fake trajectories. And the discriminator goal is to be able to distinguish between real trajectories and fake trajectories. So these two are kind of competing with each other. These are, imagine that they're playing a game, and the generator starts with a completely random distribution, generates a sequence of movements. And of course, these are random, so they're probably, at the beginning, they're not very good. So the discriminator easily would figure out that these are wrong, right? But after a while, and the discriminator keeps rewarding the generator if it could not figure out the difference between the real and fake. So in this loop, basically, the generator gets better and the discriminator keeps getting better. The loss function of this is kind of a min-max function. So the generator try to minimize the chance that generating something that the discriminator will figure out. And discriminator was maximizing the probability that it can figure out if something was generated by generator versus a real trajectory. Now, this GAN idea was there before. What sequence GAN did was basically extended this for a sequence of, and this doesn't have to be trajectory, it can be sequence of anything, right? So in this case, it was a sequence of movements. And then the challenge was that as I mentioned, you generate one movement at a time, but for discriminator to figure out something and give a reward, it needs the entire trajectory, right? So think of it again as chess. When you play chess, when you make one move, it's difficult to say that was a good move or a bad move, right? There's no reward for that one move. But if you basically look at all possible moves that you can do and what you end up with, then at the end, you can say, oh, that was, if you win, that's a reward, right? So the same thing, when you create these trajectories one point at a time, one movement at a time, then at the end, you can look at the entire trajectory and say, okay, this makes sense. This is like a real trajectory. And in that sense, you get a reward if you trick the discriminator, right? So this is basically has a big advantage because by creating only a single next step, basically say, okay, I go from point A to point B and point B to point C, and then from here, you let the discriminator basically generate all different movements, and then suddenly you get a lot of example rewards back as a generator. So it also has the advantage of giving you a lot of feedback for only a single point that you generated. So this was the main, I would say, contribution of this paper that came up with sequence scan to do this kind of generating the synthetic trajectories in this game of competition between the generator and discriminator. So after that, people basically took that sequence scan, and again, sequence scan was not for trajectories, it was for any sort of a sequence generation, synthetic sequence generation. They took that and they use it specifically for trajectory generation. So these are all sample work at the time that took the sequence scan and applied for trajectories. And GAN was at the beginning, but they also looked at other types of approaches like the Gale. I'm going to talk about our approach with Gale later. Was a similar kind of idea as GAN. And also people use VAEs, the same variation of autoencoder that I mentioned. So these are basically different data sets that they used to train these models and then generate these synthetic trajectories. But the problem or shortcoming, I would say, with all of these approaches was that they generate the trajectory, but they cannot control the generation process, right? So for example, if you have different type of like modality of transportation, so you have like walking and somebody biking and somebody driving, you couldn't control that the synthetic generator also generates these different types of modality that also generates trajectories that are walking, biking, and driving. Or if you know the moving behavior, it couldn't generate these different moving behavior, and I'm going to explain what that is. So before I go further, let me define what, because I keep using this term trajectory loosely. And there are really three different things that people refer to as trajectories. The kind of a traditional definition is that you have sequence of these GPS logs. These are lat and longs, and then you have them regularly timestamped. So basically every 1 minute, for example, or every 30 seconds, you collect the lat and long. And that's one definition of trajectory. This is relatively, I would say, generating this sort of synthetic trajectory is relatively easy, right? Because in 1 minute, you can't move that much. So you can always predict where you're going to be in 1 minute, right? So if I know your coordinate, predicting what's going to be your next coordinate in 1 minute is not that tough. So a lot of actually techniques that I showed you in the table, they use this definition of trajectory to generate. And these are the ones that usually show very good accuracy, 99% or 90% accuracy in generating their synthetic trajectories because it's a relatively easier problem. The other kind of definition that sometimes people use for trajectories is location of points of interest. So for example, you say I was at Starbucks first, and then later I was at USC, for example. In this scenario, there are two differences. One is that these are not regularly timed anymore, right? So you can be at Starbucks at any time, and then like 20 minutes later to be at USC, and then from here 30 minutes later you be at another location. And these are not lat and long, these are actual locations, like for example a coffee shop or a work. So if you want to generate this sequence, it gets a little tougher, right? Because now you don't know when is the next event happening. And basically these are not only like movements within 1 minute. So this is a little bit more difficult. And then even if you want to, so we're going to focus on this mainly. And then next, we also make it even more difficult. We say, okay, we want not the sequence of locations, but sequence of visits. The difference between location and visit is that the visit also has time associated with it. So here we say we want to be at Starbucks. You were at Starbucks from 12:04 to 12:43, and then you were at USC from 12:58 to 17. So this is basically a visit is not only the points of interest information, but also the arrival time and departure time. So this is the ideal scenario that the sequences that you want to create. And this is the more difficult case as compared to the, so we look at both of these. So basically, in this talk, first, I'm going to look at synthetic generation of sequence of location. This is just the one that they say USC, Starbucks without the time. So, and as I mentioned, the focus is on control generation. So I use the our approach to do this control generation using Gale. Then second part is also about synthetic generation, but this time the sequence of visits. This is the more difficult one, where you have arrival and departure time, and we use a transformer to do the control generation. So that's basically the outline for the talk. Any questions so far? Okay, so I keep mentioning this control generation. I said, for example, is the modality of the movement or the mobility behavior. So let me tell you what I mean by mobility behavior. So the mobility behavior is basically the reason somebody moves, right? Why you go from point A to point B and point B to point C, right? So you do that because, for example, this is a work commute. So you're going from home to coffee shop, and then from coffee shop to work, and then to lunch, and then to work, and then back home, for example. So that's a work commute behavior. You might go out for a couple of hours just for shopping, right? That's the shopping behavior. Or you might go out at night for dining and entertainment. So these are different types of mobility behavior. And knowing why you move, as we mentioned before, is important for various applications, right? So for example, at time of COVID, knowing that this sequence of movements, you go to a restaurant is because you go there for lunch, because that was you're going to work, versus you're going to a restaurant at night for entertainment, might determine whether closing that restaurant, for example, make an impact or not, right? If you're doing like construction and you want to build a bridge or kind of resurface a bridge and you want to close it down, whether the commute goes through that bridge or entertainment movement goes that bridge is a different policy, that how long you're going to close that bridge, at what time of the day you should close the bridge, and so on. So a lot of these applications care why people move, right? Not just the fact that people move from one point to the other. So the basically looking back at this synthetic generation, the idea is that in real world, you have, for example, 3 different modality of movements. You have people going, walking, biking, or driving. And then you want to generate synthetic generation, synthetic trajectories. And you don't want your synthetic trajectories all be biking, right? You want the synthetic trajectories also reflect the real world. I also want to include some biking, some driving, and some walking. Similarly, in the real data, people move sometimes for shopping, sometimes for commute, sometimes for entertainment. You want your synthetic trajectories also have some trajectories that are shopping and commute and entertainment, right? So what are the, I guess, the differences between when you want to generate these synthetic trajectories between walking, biking, and driving? But, yes.
Depends on the application I think you're using, but the location updates would differ. Like,
yeah, I mean, so for walking, for example, you go a shorter distance, right? And it's slower.
I meant also like the number of frames that's being captured. That's also going to be spaced out for cars because it doesn't timestamp it as quick.
Right, but yes. So basically, if you generate the synthetic trajectories, you want to generate it with the speed and the framing that makes sense for that modality, right? So if you don't take that into consideration, you might end up either creating like trajectories as always driving, right? So you need to control the generation, right, based on the training data. Similarly, what do you think is different between these behaviors, like shopping versus commute? How you differentiate them?
One shopping will be in a smaller vicinity, and this will spread out probably for a car.
Right. So that's one, but the other also is based on what type of location you visit, right? I mean, the shopping, you visit shopping malls and stuff. In commute, you visit home and work and coffee shop, for example. So the type of location that you visit is important, right? So if you generate this without this knowledge, without incorporating this knowledge into your synthetic generation, you might end up generating trajectories that don't make sense. Like somebody leaves home and I don't know, goes, for example, back to work and then go home, right? Without any other movements, for example. So depending on the type of places they visit, right? You want to generate this diversity of these. So this is basically this paper where we try to generate these realistic and representative trajectories. And by realistic is, of course, meaning that synthetic trajectories should be similar to the real world data that we use for training. But representative, basically, that's where we mean that we need to basically represent different types of movements, right? Whether commute and so on. So first, basically defining what we mean by trajectories. Here, we take the word and break it into grid cells, as we always do. And then we can think of a trajectory as basically the idea of a grid cell. So you started at grid cell 1, then you went to 3, then you went to 7, then you went to 8. And by kind of, this is our trick to get away from the irregular timing. So for example, here, we say that the difference, the movement from one grid to the other grid, let's say, is 5 minutes. But if you stay at grid cell 8 for 10 minutes, we just repeat it, right? So if you put 8 and 8, it basically means that you stayed there longer. So that's how we kind of deal with the irregularity of timestamps. We're going to fix this in the next one, where the timing is more important. But here, as I said, the main focus is just on the POIs, on the points of interest. And you can think of a POI as a grid cell. So for example, a context trajectory for this would be you start from a residential area, and then you went to a kind of a coffee shop, for example, in an entertainment area. So how would you add this context to this cell? How would you know what type of an area each cell is? Because that's important if you want to generate these different type of mobility behavior. So if I just put this grid and say, okay, what type of an area is this? How would you go about kind of labeling it at what type of an area is it? So you can basically look at what sort of POIs are in this area, right? So here is basically, we look at, I think, 8 different areas. So we have industry areas, commercial areas, recreation areas, and so on. And the way we decide each cell, what type of an area is this, is basically we look at the number of points of interest in each one of these areas, and we see which category of these they belong to. And whichever is the more, the majority, that would be the label of the cell, right? So for example, if a cell is tagged as education, as a blue, that area has a lot of schools and universities and so on. So that type of POI is more dominant in that space, right? So that's how we label each area. And then the idea is that similar moving behavior should have similar context. So if you have a commute, usually starts from residential area, ended up in a work area or industry area, if both two different type of a sequence have the same type of a context, then they are similar moving behavior. So you start from, and these are actually real data we use. So you start from the raw map of Houston, and then you can use OpenStreetMap or whatever to figure out the POIs in each grid cell. And then you count the category, and then you tag it. So this is how the context comes to the map, right? This is not the movement, it's just we tag each cell by saying what type of an area is this. So now we basically follow the same concept as GAN, but this is Gale. And the difference is basically instead of generator and discriminator, you have a policy net and you have a reward function. So the policy net is basically what is trying to learn why people go from one point to the other point, right? So what decision they make to go from one to the other. The rest is very similar to the GAN. So again, you have real trajectories, and this policy net generates these synthetic trajectories, and the reward function give a reward if it cannot figure out the difference, then it gives a reward to the policy net. It's the same kind of a max mean model. But now we want to add to this the context, right? We want to be able to control it. Because if you think of these as human agents, the decision-making process is based on why they are moving. If they are moving, for example, for commute, there's a higher chance that the next location they visit is a work area. But if they're moving because of entertainment, there's a high chance that the next location they meet is a restaurant area or a shopping area. So here are basically, if you think of this as a reinforcement learning, it has basically, these are the components that you have. So if you look at the real world trajectories and the moving behavior labels, so that whether this is commute or whatever, you want to generate these synthetic trajectories by retaining these moving behavior properties. So the state is basically the history of the generated trajectory until the last state. So basically, what are the places, what are the sequence of places this guy went to until now? The action is that what they're gonna do next. So this is, if you think of chess, is all the movements that up to the point that they got you to this grid. And the action is that what you're gonna do next, which grid you're gonna go next. And the state transition basically is make the move, make you go from the state to the action, given the action to the next state that you want to go. And policy network is how you choose the policy action, which action you use, which state you go, given the moving behavior. And then at the end, the reward is that evaluate this decision, whether the action that you made was consistent given the current state. So this is the general framework. I'm going to go through each kind of step one at a time, but mainly this is, you can think of this part as the generator. Basically generates the result of this part is an action. It's saying that, okay, I'm given where I was, I'm going to go here. And then this part is looking at this action in the context of all the previous action and the context. And I want to describe this a little more, deciding whether this was a good action or a bad action. So whether it should be rewarded or not rewarded. And this reward goes back. And then as a result of this loop, you generate more and more realistic sequence of actions. So the first part of the generation is based on the context. So it mainly look at the context. It doesn't look at what cells exactly they've been to or what location they've been to, but what type of a context they've been to so far. So it looks at the past context, and given the past context, it decides what should be the next context, right? Doesn't say where exactly the next move should be, but what type of a place this next move should be. And there's a parameter that you can basically say whether how important is this context. And if you increase the parameter at some point, all the different contexts would have the same weight. So if, in a sense, you're not looking at context at all, right? You're just looking at the location. So the second part is the actual location. So it basically says, if you've been in these specific locations in the sequence, what's going to be the next location you're going to go to? And this is going to predict the next location, the specific grid cell that you're going to go to. The third one is the part that actually become more important in the modality piece. It basically says that, because if you look at this as a completely random with some probabilities of each cell, then if somebody's here, just based on these two, you might basically say, okay, the next location this guy should go should be here. But the problem is that it might not be possible from a distance consideration that somebody go all the way from here to here. So this state transition is not realistic because it's just too far, right? So this is probably the higher probability area. So you can think of this as a Gaussian around the current location, showing the probability, and the chance of somebody going all the way here is very, very low, but the chance of being in these locations is higher. Now, the question is that how would you learn about the parameters of this Gaussian model? How do you know what's the mean and the variance of this Gaussian? Where you calculate it from? So here is actually what we've done was basically a dynamic one based on the past movements, right? So you look at the past movements and based on that decide that what the next movement, how far you can go. And based on that, you have this average and the variance, and based on that, you decide that, okay, this is just too far. So you give lower probability. So these three things, each give a probability to a cell. Yes.
So what you're learning here is based on recorded data you're trying to model that.
Based on the real data you use for the training, right?
And whenever you're trying to create synthetic data, you're trying to like mimic that.
Right.
Would you also be able to do it like without that?
Without
real world data, like just synthetically creating it from something.
I mean, at some point, but you need some real data to train the model. So you can't start from nothing, basically. So the real data just guide you that what real trajectories typically go from one location to location, how far they go, and what type of context they go through.
Then this is kind of like a little bit too data dependent.
It is very data dependent, yes. So it's a data-driven approach. The idea is that you give a bunch of real trajectories that you have, and it generates synthetic trajectories that follow the same. But you try to control it, because if you don't control it, as I said, it might suddenly generate weird trajectories that are all like biking, or they're all doing commute, going through certain type of context, missing some other context. So here we're trying to force it to be more and more similar to the diversity of the real world trajectories.
You also did any analysis? Did you also do any analysis on the distribution of these activities? Do they also follow like version distributions?
What do you mean by distribution of the activities? You mean like the
proportion of biking to cycling to something?
Oh.
They follow the normal.
No, I mean the data set can have any distribution, right? The idea is that if the real data set that you have certain distribution, you want the synthetic one follow the same, right? So it doesn't matter what the distribution is, right? Like, I mean, in the experiments I show you basically how we compare. So basically the idea is that the more similar your synthetic generation in diversity and accuracy to the real one, the better. But basically, these three things each make a decision, right? So this one basically says, given the context that this guy has been through until now, I predict that it's going to go to an entertainment cell. So all the entertainment cells would get higher probability, right? This guy would say, based on the locations this guy visited so far, I think this is going to go to this location. So that those locations get high probability. This is the same softmax, the same output model, right? And then this third guy say, based on the distance and the speed that this guy is doing stuff, I predict that these are the cells with the higher probability. And then you take these three and fuse them together. And as a result, you get the probability of the place that satisfies all three, right? You find the place that both in the context, in the location sequence, and in the distance is the best one to take next. And you recommend that as the next location. That's, I already mentioned this. So this basically use some sort of element-wise multiplication to generate the final location. And that location now goes to the sequence. And it basically say, here is the sequence of so far. And the discriminator basically needs to make two different decisions. First is that how good is the location, and then how good is the context, right? And based on these two, again, do some sort of a aggregation and generate a reward. And the reward, so there's a reward from the moving behavior and a reward from the discriminator, which is the actual location. And this is a learned parameter, basically. So this reward would go back and would basically train the model. So as a result of this, you would say, okay, whether I predicted the right thing or the wrong thing. So this is the part, so the experiment. So again, the data was the Veroset data. Again, this is real data from mobile phones. We did it for two cities, Houston and Los Angeles. The date was March 2020. That's the time we got this. This is a spatial grade that we built. Basically, you can think of it as the same. Basically, you have the space and you have the time. So it's a 3D grid. The spatial resolution, this part was 200 by 200. The temporal resolution was every 1 hour. Every 1 minute. And then the POI context was basically taken from SafeGraph, which is basically saying what context is each cell. And this is fine because SafeGraph actually uses Veroset data, so they are aligned. SafeGraph is just the aggregation of Veroset data. So the evaluation, as I mentioned, is basically, there are two types. The one type is looking at the entire data statistically. So it looks at the entire real world trajectories and say, for example, what's the probability of visiting a specific cell given the real data, right? And then the synthetic data also basically have what is the probability of visiting a specific location. And then you get these two distributions, the real distribution and the synthetic data that you generated, the distribution there, and then look at the JS divergence, which is basically compare these two distributions, and the closer they are, the better, right? It basically means that the synthetic data that you generated are more similar to the real data that you use for the training. So another aspect of this is that not only how many people visited a specific location, but the time aspect as well. How many people transition from this location to that location, right? In the real data, and how many people transition from that location to this location in the synthetic data. And those are also two other distributions that you compare. So you have two comparison here for the statistically. And then you also look at each individual trajectories that you generated for some statistical characteristic there. So for example, you want to see what's the typical distance traveled by a trajectory in the real data versus the synthetic, and you want them to be similar. Or number of distinct visits that each trajectory had. And again, you want these to be similar as well. There are no kind of known set of metrics. These are the ones from various papers that we picked. Actually, this one, the transition, I think this was first used in this paper, or maybe another paper, but still from our group, that look at the transition going from this location to the next location, which is important for these trajectories. And these trajectory level stuff are all ours, basically, because we want to not only statistically, we show how good is our synthetic data versus real data, but also single trajectories, how much they are similar to the ones that were in the real data. So we compare this with various baselines. MoveSim was state of the art, I think, at the time. And if you look at, so these are the two cities, and these are the metrics that I mentioned. Distance, radius, and duration is the single trajectory statistics. PR is the probability of a single cell visit, and PR1, R2 is the probability of going from this cell to that cell. And the values is the JS divergence between the distribution, so the lower the better. So for example, this is a really good value for this, basically meaning that the real data and synthetic data have a very similar transition values. What else I think I have some animations here. So one kind of one good observation here is that in individual trajectories, the distance of the trajectory and the radius, our results were way better than the state of the art if you look at the differences. And I think this is because of the inclusion of these modality and the mobility behavior. Because if you think of it, the distance that you travel in a trajectory, it really depends on what type of a modality you're using, right? Whether it's walking versus driving, that determines the distance. So by incorporating this diversity, not only you get similar diversity, as I'm going to show later, but also you get more accurate trajectories generated, both from the distance and radius. The other thing is this transition, as I mentioned, is much better than the others. And I think, again, this is because we cluster these modalities, right? This mobility behaviors. So the chance of basically going from one to the other, the probability of going one cell to the other is determined not only by your previous location, but by the reason that you're moving, the mobility behavior context. So that helped. To see basically how diverse the trajectories were, we basically used, we have the real data, which is the actual mobility. So there are 5 different clusters of moving behavior. And then we look at the data generated by sequence scan. That's the first technique that I mentioned. MoveSim was the state of the art, and this is ours. And ours actually had the minimum gap between the real data and the and ours in each cluster. So the percentage of the trajectories, for example, that fall into this cluster between real data and ours were much more similar than the others, which basically means that our diversity of mobility behavior was much closer to the real data than these other techniques. And that's not surprising, because none of these others actually take the mobility behavior into consideration when they were generating the trajectories. And the whole point for us was to do that. So this is not that big of a surprise, because we kind of explicitly try to generate trajectories to follow this distribution. But what was the surprise was that as a result of that, we actually got more accurate as well by keeping this diversity in the data. So that's the first part, which is basically, as I said, we don't care about the time, we only care of the sequence of the visit. And the scale approach would basically allow you to do that and become more accurate by adding the modality and mobility behavior into the model. The second part is kind of making this a little bit more difficult, as I'm going to explain later, that where we have visits. And because of that, we basically use we still do want to do control generation, but it's a different type of a control. And instead of the GAN model, we basically use a transformer model. Again, these are the papers for each, if you want to read more. So as I mentioned, the the sequence of visits not only have the POIs, but we also want to generate the arrival and departure time for each visit. This is a very difficult task because not only we want to say that you're going to go from Starbucks to USC, but we want to exactly say how long you're going to stay at that location and at what time you're going to leave. So this is a much more difficult. Because also, if you think of it, these are, as I mentioned, just sequences, which is very similar to sequence of words, for example. But time is not, we cannot basically in an autoregressive way predict time, that what's going to be the next dwelling time at a location. So this was a more recent work. So there are more work came out. Again, a lot of them were focusing on location logs, which was the easier scenario. There were some that started looking at POIs and use even large language model. I think Professor Mokbel, I think, went through some of these where they're using LLMs and others to generate these sequences. But almost all of them, not almost, all of them only were based on POIs. None of them basically add the time aspect to generate visit sequences. So none of these can generate the dwelling time, how much you stayed there, and what time you left, what time you arrived, and what time you left. So basically, in our case, the problem that we want to solve is that I was at this POI from 8 p.m. to 7 a.m. And then I went to this POI from 8 a.m. to 12 noon, where I'm going to go next, right? And what you expect to see is this sequence generated after that, which basically not only say what location you went next, but what time you went there and what time you left. So this is basically the problem definition. And again, we can put a grid on the space. And in this case, we actually use the Uber gridding. So it's not rectangles. This generates a better coverage of the word. And for each grid, we basically assume that it corresponds to a single POI. So it's a small grid that corresponds to the type of a place that they visited. But at the end of the day, you can think of this as just IDs. So it's just basically sequence of IDs. But the focus is more on the arrival time, departure time to that cell. So what are the challenges? The first challenge is the temporal challenge. So here, assume that this is the actual distribution of time that you stayed at a location. So let's say that, for example, this is a restaurant or it's a coffee shop, let's say, and then sometimes you go to the coffee shop and you stay there around 5 minutes, right? This is where you go and pick up your coffee and leave, right? But every once in a while, you go to that same coffee shop and you stay for an hour because you go sit down and do work, right? And have your coffee at the coffee shop. So you have kind of like two different distribution of the time you spend at the coffee shop. You have a distribution which is around 5 minutes with some variance, and then you have another distribution that's like 1 hour with some variance. How do you think is the best way to model this distribution? I mean, this looks like a Gaussian, right? This is like a normal distribution, but you have two of those, so it's kind of like a mixed Gaussian model with two components, right? So each component has a mean and variance, and also the fact that you have two components and the weight of each component. So if you have these, you can basically know what's this distribution. But if you use now autoregression, so you don't consider the actual distribution and basically say, okay, what would be, how much time I would spend in this coffee shop? If you use it in an autoregressive way, what do you think it would give you as a result? I mean, if you have this distribution and you pass it to a loss function that does like regular autoregressive and use cross entropy and so on, the typical transformer. It always finds actually the the expectation, right? And the expectation gonna be some duration that is neither 5 minutes nor 1 hour. It's gonna be somewhere there. And this is not correct, right? I mean, you never stay at this coffee shop for 20 minutes. Even if you do argmax, so you change it instead of expectation, doing argmax, it's always gonna give you the 5 minutes. It never gives you this one. So that's the challenge with predicting time, right? If you ignore the underlying distribution and just based on the samples you have, decide to do the autoregression, it will always give you the wrong time. So you somehow need to, instead of doing basically just looking at the samples and decide what's going to be the next sample, you need to learn the distribution itself. So that's basically what we did. So we tried to use the transformer to learn the distribution rather than predicting the next sequence or the next time. And when I say we need to learn the distribution, it just needs to learn, we assume it's a Gaussian, right? It needs to learn basically how many components and what's the minimum. Actually, the components we also fixed, I think, in the experiment. So it only needs to learn the mean and the variance for each component, and then the weight of the component. So the output of the transformer are those attributes. The other challenge is also very similar, which is the spatiotemporal challenge. Here again, the idea is that you, at lunchtime, basically, you either, sometimes you go and get food from food truck, so you spend 5 minutes, 10 minutes there because it's quick. You just get the food and leave. But sometimes you go and sit down at a restaurant for 2 hours, right? So here it's a very similar concept, but it depends on where you are, right? So somehow, if I know the location, I can do a much better job deciding that how much time I'm going to spend there, right? So the time you spend somewhere, the dwelling time depends on the location itself. Again, if you do a space independent expectation, you just don't do this. So you say, okay, I'm just going to predict the amount of time I'm going to spend without knowing the location independently, then you're going to end up kind of predicting the duration that doesn't make sense based on the expectation, right? So, or it's the same thing. Again, if you do argmax, you always predict that you spend 10 minutes during lunch, but that's not correct either. So basically, the way you want to model this spatiotemporal joint modeling is say that given my past visits, so this X prime is a sequence of places I've been before, right? Given this past visits, you want to say what is the probability that my next visit is X, right? And then this next visit X has 3 components, right? It has a region, which is basically the location, one of those cells, right? It has an arrival time and it has a departure time. So given X prime, given the previous visits, you want to predict what region you're going to go, what time you're going to arrive, and what time you're going to depart, right? So that's what you want to calculate. Now, if you look at what would be the loss function for this, the loss function is the usual negative log likelihood. So this part is the same as always, but now you want to actually take this X and use the chain rule and kind of expand it to the probability of going to this region R given X prime, and then probability that you arrive at this region R given X prime and now R. This is that dependency that I said, it depends on the region. And then given the region, given the arrival time, and given the previous sequences, you want to see what's the probability of departure at this time, right? So you have these dependencies, and this is all very neatly captured because all you did was you took this, replaced X with these 3 components that you want to learn, then you use the chain rule and created this. And then if you do a log of this, what would happen, this is a joint distribution, So this is the region, this is the arrival time, and this is the departure time that you want. And again, so when I say the T of A, I don't want to actually calculate the specific time, arrival time. I'm only interested in finding the parameters of the Gaussian model that is underneath the distribution of time. That's what I'm trying to learn. And when I say departure time, again, the same thing. I only want to learn the parameters of the distribution underlying. So if you do a log of this thing, basically it simply becomes the sigma, because log of A multiplied by B multiplied by C is the log of this plus that, right? So this becomes this, and this is simply your log function, your loss function. Do you see anything interesting about this loss function? There is no hyperparameter in this loss function. It's a very elegant loss function because you basically don't need to learn any parameters or any hyperparameter. It's simply three different log likelihood and loss, and each one of them is basic. So this one is a simple learning of what's the next sequence. This is the most similar to what transformers are being used right now. So this part is nothing interesting. It basically says, given the previous sequence, what's going to be the next sequence, given the all possible sequences. This part basically says, now that I figured out the location and I know the previous, now give me the parameter of the Gaussian model underneath this arrival time. And then I can figure out the arrival time by sampling. And the same here now, given that arrival time distribution, their location, and the previous sequences, give me the parameters of the Gaussian mixture model that's underlying the departure time. So that's basically how you would be able to predict time. So the way this is done in a transformer is basically, the rest is just basically engineering. So you do the same thing. I will tell you how we do encoding the visit sequences and use that to predict the region. So for example, if you have this sequence and you want to predict basically what's coming next, you use space to vec. This is, if you're not familiar, don't worry about it. But what it does, it basically takes the location and generates a vector, because everything and every entry to the transformer should be a vector. Time to vec gets the arrival and the departure and generates vectors for that. And region embedding is basically embed the region with all the information you have and take all these into the positional and transformer encoding. Positional basically says in what order the location and the visit happen. And this generates basically your hidden state once you pass it to the encoder. And then you take this and actually we do the simple linear, not even MLP, and then do a softmax. So the softmax basically give the probability of what's going to be the next location for the entire space. So it's a simple, so you can think, even though it's a grid, you can think of this as a sequence of words, right? And it gives you the probability of what the next word would be. So in this scenario, basically you say, this is my predicted region because it's the higher probability. So that's going to be my next location. Now, given this location, now that you figure out the type of the POI, this is a restaurant or whatever, then you pass this into the next step, which is supposed to predict the arrival time. So given this region, you again take these attention of, so this part basically, if you're familiar with the transformer, what it does is that it basically says, what given this region, what type of a dwelling time attend to this region, right? So what are the possible dwelling time for this region? And this, as a result of this, again, you don't predict a specific arrival time. What you end up predicting is the parameter of a Gaussian mixture model, the weight of the component, the mean of each component, the scale of each component. Scale is the same as standard deviation. And this would give you just this distribution I'm going to tell you how later we're going to use this distribution. And then taking that distribution, doing a time to wait, you do the basically the next step, which is basically now you have the arrival, you get, sorry, the next step is the same, basically the same way that you take the region and you calculate the arrival time, you get the region and arrival time to calculate the departure time. So you end up, your transformer basically generates the region, the arrival time, and the departure time. Now for the arrival, for the region, when we want to evaluate it, we can do the usual accuracy at k. Basically say what is the, if you have the ground truth, you can say basically whether you predicted this correctly or not, right? But what about the time? How would I know if the arrival time and departure time are calculated correctly? Because, I mean, I got a distribution. I don't have a specific value for time. The output is just says that here is the Gaussian mixture model for arrival time. It doesn't say what exactly is the arrival time. So how would I mean, the ground truth is an actual arrival time. How would I know, how would I evaluate whether my Gaussian mixture model is good? Yeah, one idea is to get the mean, but the mean is basically, I mean, if you're far from the mean, you would get 0. But yeah, something like that. So basically the idea is that, let's say that this is, again, we kind of came up with this because we wanted to evaluate it. So the same way that you have a top K accuracy, we came up with a top T accuracy, and the top T accuracy is that interval basically. So we say that if this is the time that the ground truth, oops. Oh, do I have animation for this? Oh yeah, I do. So let's say that this is the model, this is the distribution that you predicted. This is the Gaussian that you predicted for the departure time. And this is the ground truth. So the ground truth was here, right? It's not the mean, but it's not that bad either, right? It's kind of in a high probability area. So what we did is that we look at the minus plus t. So this is the same that you have accuracy at k. K is like a parameter. You also have t. So you look at this interval and you see that what's the area under the curve for that interval. The more, the better, right? So that's basically how we evaluate whether this distribution that we learn is good or not, right? So we, for the experiments, we basically had 2 different data sets, GeoLife and Mobility Sim. These are the statistics of how many agents and how many regions, how many visits, and so on for each of them. As I said, we use the Uber H3 index cells. Those are those hexagons. And this don't worry about it, but because this is going to come clear in the next part. But basically, we first look at the next visit prediction. So the idea is that we have these 2 visits and we want to predict the next visit. And again, for each visit, not only we want to figure out the location, but also the arrival and departure time. And we compared with, these are the 2 data sets, we compared with 2 other baselines. Neither of these baselines, as I mentioned, calculate the dwelling time, the amount of time you stay at the place. GetNext actually did have something to calculate the arrival time, but it uses the auto-regression to calculate the arrival time. So if you look at the results, so first of all, nobody predicts the departure time, so nobody predicts the dwelling time. So this is the results we got for the different values of p plus minus 10. And again, I mean, it's not perfect, but it's not that bad either. So there are a lot of space for improvement if you guys can come up with a better way of predicting the dwelling time, because there's a big space for improvement, especially at plus minus 5. Plus minus 20 is not bad, actually. The arrival time was, as I said, there was already a competitor, but because it was using auto-regression, it was really bad. So here, actually, for arrival time, especially at p plus minus 20, we did very well, especially for the mobility sim. which is kind of a denser data, so you have more examples. The GeoLife data is very sparse, so it's very difficult to learn basically. But for mobility sim, these are really good values. The accuracy at 1, 5, and 10 and 20, I think we did okay. But again, that was not the focus, but we did, because that's just simply we use transformer. So we did kind of either us was or get next, which was kind of the state of the art. So we were very close to that, if not a little better. But again, the most important part was the contribution was for the arrival time. But all of these was in the context of next visit generation. But I told you, I kind of promised you that I look at this in a controlled generation, right? So what was controlled here? We just generated synthetic visits, right? So far there was nothing. So basically we said the first limitation of everything up to this approach was that nobody can generate visit sequences, so we did. But we also looked at generating trajectories with no visit. So this is the control part. So the control idea is this, that basically instead of figuring out what's going to come next, we assume that you already know that you were at home and you were at work and then you are at home. So you already know these 3 visits. You just didn't know, you want to fill the gap. Basically, you want to say, where did you go in between? And in between, it can be 1, 2, or 3 visits or many visits, right? So we don't tell you how many visits. You need to figure that out and fill the gap. So this is a different problem than next visit prediction. You need to fill the gap between the visits. So if you use techniques like BERT, for example, if you're familiar, they cannot do 2. They basically just fill the gap with 1 word, right? So you can use that, but then you can only create 1 visit. If you use techniques that are causal, like GPT, it basically try to find what's coming next. But then what's coming next, again, is a visit with the time. So it might conflict with what you already have, right? So it's going to overlap with what you already have. So it's going to mess up your gap. So neither of these techniques can be used as is for this control generation for fill the gap part. So our approach actually is not that sophisticated. So that's why I just put that at the end. We find this paper, which was for text infilling. And the approach that they took was that they had the same problem. So they had this problem that they were missing word in the middle. But what they've done is that they changed that into a causal model by adding certain tokens. So basically they said, this is basically what is missing. And now these are the answers and this is the end. So it's not like that they actually moved this here. They still moved it towards the end, and you can still predict it as a next visit. So let me kind of show you how it works. So here is basically now, this is not next location prediction anymore. This is fill the gap. So you have an extra component here before the previous components that you had. And this would like restructure this sequence in filling. The way it does it, it basically, as I said, use the text infilling. So the text infilling, the input was like she ate something for something. And this can be like 2 words, in this case, leftover pasta, or maybe 1 word like lunch. And they wanted to do the same problem and they didn't know how many words are there. And they couldn't use BERT or GPT as is. So the approach they did was that basically they created this as if this is a causal. So basically they said they put these tokens in and then say the input ends. And now this is the answer ends. And then the second answer, the answer ends. So this becomes the training set. So the training set is already, it's not in the form of this with the missing. The training set is already in the form of 1 word at a time with these specific tokens. which is for missing and the input ends and answer ends. So when you do the prediction, you still predict one word at a time or one token at a time. So given this, so this is your input, then your model predict, okay, the next thing is leftover, all right? And then the next thing is pasta. So it's still doing one word at a time. And then answer ends is the next token. And then the next token is lunch, and then the next token is answer end. So it's still predicting in a causal fashion. So we basically can do the same thing here. So we restructure this. So instead of this being in the middle, we basically say now what we want to predict the next visit. The next visit is going to show up here, but it's actually here, right? So in a causal way, you predict the next visit and then the end of visits. So that way you can basically use the transformer as is by restructuring it. So when we did the control generation, there was nothing out there that does the control generation for synthetic data. So we took getNext, which was the approach that did best in the previous one. We modified it the same way, so it can use this restructuring as well, and compare it to TrackGPT. And again, for accuracy-wise, this is now the accuracy of filling the gap, not the accuracy of next word prediction. And it, again, worked pretty much better than getNext, even after the improvement with the restructuring. But again, in time, it was pretty bad. So this is, again, the time part is the most important part here. I already mentioned that. So to summarize, basically, this is the improved the temporal accuracy a lot. It had this spatial temporal joint modeling, which I think is very new. And then this concept of the temporal GMM was very interesting. And we used it for different data set, different tasks, and different stuff. So at this point, 15 minutes?
Yes.
Okay. So I have a bunch of slides on open problems because this is a relatively new area. So I was thinking if you guys looking for a PhD thesis, there are a lot of open problems here in the control generation. So, and this is actually a topic that is very much of interest to industry. So this paper we submitted to Six Spatial as a vision paper, but this is in collaboration with folks at Google Research. And what I'm going to talk next is basically presenting this paper. This paper hasn't appeared yet, but and a lot of these are actually coming from Google as what sort of a interest they have in this. So the idea is this. The idea, I mean, you guys probably already know about these foundation models for NLP and computer vision, like ChatGPT, for example, right? And the promise there is basically you have a model that you pre-train it once. For example, you pre-train it for this next word prediction for ChatGPT. And then the same model can be used for a lot of tasks. It can use for translation, for example, it can be used for question answering. So there are all these different tasks that you can use the same model, right? So you don't train it again and again for different tasks. It's just train it once, pre-train it once for next word prediction, and then use the same model for this task. So the question is that can you do something similar for mobility data, right? So we keep mentioning there are all these different applications, or we call these downstream tasks. Is it possible to pre-train the model once and then use the model for all these different tasks? So that's basically the idea. And in order to build this foundation model, of course, you need the traditional stuff. You still have images, for example. So the same kind of computer vision approaches can be used. You still have text. So the previous NLP type approaches can be used as well. But what's kind of new and what's different is these kind of sequences and movements, right? And the idea is that how you would get this into the model, right? And how your foundation model can learn from this sequence of movements and so on, so that it can kind of solve all these problems with a single model. And these problems are very different. So for example, I mean, recently we look at very interesting downstream tasks like routing. So like shortest path or fastest path calculation, how you go from point A to point B in the fastest way. You guys use Dijkstra or A-star algorithm, or if you're familiar, there are contraction hierarchies and other techniques used by industry to do this fast, right? So these are all algorithms. But if you have a foundation model, actually, the model can predict one segment at a time and tell you what's the best path based on the previous trajectories it's seen. So suddenly you solve very algorithmic tasks using a foundation model. So it can be pretty revolutionary if you have such a foundation model, right? So imagine you have a foundation model, you train it with all the trajectories, no map matching, no traffic calculation, no forecasting, none of that. You just train it with trajectories and say, now I want to go from point A to point B, and it generates one segment at a time. It finds the fastest path for you. And there is no underlying algorithm. It's just a model. And you can do this for a lot of these applications. So the idea is that single model can do all of that as a vision. I mean, I don't have the solutions before you start asking that kind of questions. But that's the idea. For the fastest path, I do have the solution. I mean, that one we published, but
regarding the avenue, I mean, for people students starting out a PhD, they need lots of resources, right? Like data and GPUs to do this kind of a finding. So what is the approach to this?
collaborate with Google Research.
With Google Research. Okay. So that's it, basically.
Yeah, I mean, the data is actually becoming more and more available. I mean, there's this company now called Dewey, DWEY, and they have some free data for academic research. And then you can buy data as well if you have a funding that allow you to buy data. And they have very good, like they have this sequence of POIs with visit durations. So they have the data I need, for example, very specifically with POIs, start time, end time, all that. And they're also, we have this project that was just stopped that as a result, there are multiple groups and they're generating simulated data that are realistic. Andreas also is part of that. And they are publishing their data, their simulator. So you can generate, I mean, these are not real, but they are simulated data, which is generated from real data. So they are as good as it gets. So data becoming available more and more. GPUs and stuff is going to be always the challenge. Yes.
Do you have any intuition on what the size of these foundation models need to be in order to be competitive with algorithms?
Yeah, that's a very good question. No, I mean, there is no, I mean, we are not there yet. I have slides that basically what are the open problems, but the size of the model, I have no idea.
But we could estimate it, right? Like based on current hardware, it should be, let's say, roughly ballpark, it should be around 200 million parameters or something. Then we already have some threshold to work towards this. And if we overshoot it, then we have to optimize the heck out of it in order to be competitive with industry or algorithmic solutions. So is there anything, any such estimate being done?
Not that I am aware of. No, I mean, as I said, I mean, there are multiple steps even before that to solve this problem.
So what would be the pre-training task?
Yeah, so that's another good question. I mean, currently there. I don't know how much of this I can tell you because it's a Google thing, but there are two types of. So the one type of a training task is this next location prediction, but the way. So the next location prediction the way everybody use it is to generate, basically the downstream task is also like synthetic generation or so, which is basically next location prediction. But another way of looking at it is that the idea is to find an embedding for a POI.
So
And
that I think Google already has a paper, right?
yeah, but they
have-
don't have a
oh,
solution
that's
to it.
the-
They just, the GeoFM
Yeah, I
thing,
thought
yeah.
they have the embedded.
No,
for
that
POIs.
embedding, yeah, but that embedding is basic. The idea is that how can you learn from visit sequences?
Okay.
That
Oh,
how
one is not
people-
POI. I guess that one is the image based on the image, satellite image.
Yeah, but you can do embedding of POI based on static information of the POIs. But the idea is that can you learn better embedding if you know how people move from one POI to the other POI? And that would generate a generic embedding for these POIs can be used for any downstream task. So not only so you can learn about the POI just by information about the POI itself, like it's a Starbucks, it open at this time, closes at this time, and so on, right? That's one type of information. Then you can learn about the neighboring POIs of this POI, because a Starbucks that is in the university has a different embedding than a Starbucks that is in the middle of a entertainment area. So the neighborhood would add another layer of embedding. And then you can learn that, oh, usually people go to this Starbucks at this time, so that would help with visit patterns. So that's another embedding. Usually people go to, after the Starbucks, usually people go home, right? That's another, and this is coming from the mobility now. So the idea is that if you can keep adding these layers, you generate a very powerful, rich embedding for that POI that can be added to everything else you know about these locations, including the images. But again, I mean, these are all at the very
But
kind of-
what is the eventual application to this? I mean, on top of what is
the
already
eventual
out there?
application is basically these any downstream task.
Yeah,
from
but what are
routing,
these?
routing, traffic forecasting. There are a bunch of industrial ones that if I tell you, I can't to kill you. But I mean, okay, fine. Well, one of them is like opening and closing time of places.
Oh, okay.
Um,
Which is currently like kind of
manual.
bot information, I guess.
Yeah, but it's a lot of manual work
It's,
there.
yeah, so manual information that
Right.
is bought in terms of data sets
Right.
that they acquire.
Right. But they need to also update it.
Oh, so like crowdsourcing this
Yeah.
kind of info.
It's even worse than crowdsourcing. You call up the restaurant.
I mean,
what time you close.
automating the manual laborious work of
Right. Right. That's why the industry is
learning this.
Right.
Was it learning about opening and closing time of different POIs?
It can. I mean, if you have a foundation model that has such a rich information about the POIs and where people visit, it can know when the POI opens and closes as a possible downstream task. But 6 minutes to go for one slide. So, but what are the challenges? I mean, so these are the application and motivation. I think that's there. But what's for the students to work on, right? So what is interesting technical challenges? So one of the challenges I always kept hand waving about these cells and POIs, but the real question is that if you think of a transformer, you have a fixed vocabulary. You have like 6,000 words, not 6,000. How many words they have? 60,000 words or whatever, and that's the dictionary, right? So everything is based on that preset of words. In this scenario, what's your vocabulary? What are the words? And this is not as simple as it looks. So a lot of people make this observation that, oh, words and sentences are like locations and trajectories, but that's not true, because what is the location? What are the words in a trajectory? And the problem is that if you look at, for example, the words, everybody uses the same words. All the sentences have the same words. So the words have a lot of repetition in different sentences. But if you look at trajectories and suddenly you put these cells to be very fine granule cells, that, for example, you have this building as a cell, then, I mean, this building probably have a lot of trajectories, but I mean, if somebody's home, there are not that many trajectories that go through that word. So you don't have enough training, enough repeated usage of that word to learn anything about it. If you make it very coarse, these cells, then you do have a lot of repeated usage. But then the problem is that you have this internal fragmentation error because you don't know which area within this cell was used.
Cyrus, I have the question like in respect to the XY, the location, because you refer to it in an abstract way, but in reality, we know that mobile phones, use this geolocation databases. So, which means that the GPS rarely fires up. So it's mainly, either, Wi-Fi localization, cell tower localization. 2 kilometers is the one, like so you have this error bound. So you have all these trajectories that basically are like with either an envelope of 2 kilometers or 300 meters.
Right.
In some rare instances, when you're driving with let's say with a car navigation system, it's a 1 meter accuracy system because this is the time the device fires up the GPS. All the other time it's so. And then the question is, I mean, how does this affect the overall idea of? I mean, because all of these ideas.
This is one of the challenges, right? So there's no easy points. And then, I mean, usually people say, oh, we just snap it to a POI and we just use the POI.
You need to do a map matching thing.
Yeah, but the snapping to the POI has its own problem because just snapping to the closest POI is not the right POI. And that by itself is a challenge, right? That what POI this guy actually visited. And that's interestingly, we have another submission that can be solved by this foundation model. So the foundation model, if you have the foundation model, it can basically tell you, because it knows the visits before, it knows the visit after, it knows the time of the day, it knows where you usually go. So giving an inaccurate GPS, it can tell you which one of these POIs is most likely you visited. So it can do the POI. So that's another kind of downstream task. So, and these downstream tasks are important downstream tasks. These are open issues with not just for academia, but for industry. I mean, a good way of figuring out where you visit is not easy. Even industry doesn't know. So they just estimate. But if you have a model that can give you the exact one, this scale and resolution also, I already kind of mentioned it. This we already discussed with the and this has also the multiple resolution. So I just hand wave around the duration, but you have this depending on whether it's a second, minute, days. Also, you have these recurrences. So you go to the same place every Monday. How can you capture that, right? That kind of a thing. Privacy, we already mentioned. A lot of these, again, I hand wave that we just have a synthetic data, so it's private. But as you heard in the morning, just being synthetic doesn't mean it's private. So you need to make sure that you cannot actually have MIA and figure out what actual data was used. And then another, so with the words, basically you learn something and you're done. But with the trajectories and movements, you learn something about one city. It's going to be a totally different thing in a different city. So how are you going to do this? Are you going to go keep learning for each city, or do you want a way of transferring things? So you just learn one city and transfer it based on the attributes of the other city. So that's another challenge. Okay, I'm going to finish. So this is basically, including Professor Xiang, there are a big group of people helping with this project. Many of these fundings are gone at this point because of the new administration. This one just stopped last week, 2 weeks ago. But hopefully, I guess with other sources we can continue. But if you guys interested, contact me. I'm happy to work any free students, given the lack of fund. All right,
So
thank
let
you.
us thank the speaker. Do you have any questions? No? Then I would like to thank you all again.